See, in the last few classes, we were talking about the 2D transformations. We were talking about the 2D transformations. In this, we have studied about translation, rotation, scaling. After that, other 2D transformations like shear and um, reflection. And also, when we were talking about the two-dimension rotation, so we considered two cases, like you are rotating a two-dimensional object around a pivot point. So for that, like steps like the object was like the object would have been in certain coordinate system. So you will consider that pivot point. You'll move that pivot point to the origin. After that, you'll perform the rotation about the origin, and then again you will move it back the object or that pivot point to the earlier position. So the sequence of operations was like this: move the object, translate the object from that position to the origin, rotate the object, then again move it back to its original position. So the same thing with scaling also. You want to scale an object from a fixed point. You want to scale an object from a fixed point. So what you were doing, you were taking that fixed point, you are moving that point to the origin, then you are performing the scaling operation. Once the scaling operation was performed, then you are moving the object to the initial position, the same position from where you just translated. So now the same concepts we are considering in, we are extending that. So now we are talking about two-dimensional scaling. So now we are talking about two-dimension scaling. So how do we scale an image or an object with respect to two dimensions? So see, for example, for example, if we have parameters, if I have parameters like sx means scaling along x direction, sy means scaling along y direction. So the parameters sx and sy can be used to scale the objects along the x direction, along the y direction. But you want the object to be rotated in other direction. So in our example, I want to rotate this object in, I want to scale this object in s1 direction, s2 direction. So how do we do that? So in order to scale an object in s1 and s2 direction, one thing is, first thing is you should rotate the object. You should rotate the object. You should rotate the object. You should rotate the object by an angle theta, such that it will intersect with the coordinate axis like x-axis and y-axis. So first thing is you can scale the objects in other direction by rotating the object to align with uh, the coordinate axis. Meaning here I should rotate, here I should rotate this object, here I should rotate this object with respect to an angle theta, such that s1 will coordinate with x-axis and s2 will coordinate with y-axis. Then you can perform the scaling along sx, sy. So like that. So we know that parameter sx and sy will denote the scaling along x and y directions. So if you want to scale an object in other directions like s1 and s2 in our example, so you can scale that object. For that, the first thing is you should rotate the object to align the desired scaling direction with the coordinate axis. So after it has been aligned with the coordinate axis, you should perform the scaling operation. You should perform the scaling operation. So in our example, to perform the scaling, first thing is I am rotating an object. I am rotating an object such that I'm rotating an object by an angle theta, such that s1 is coordinating with x-axis and s2 is coordinating with y-axis. So it will be like this. The image is like this. No, the image is like this. The image is like this. So I'm rotating it by an angle theta such that the S1 will come along x-axis and S2 will come along y-axis. I'm performing the rotation by an angle theta. So first thing is I'm performing the rotation so that the S1 and S2 will coordinate, or it will intersect with x-axis and y-axis. So after that I will perform the scaling along x-axis through sx, and I will perform the scaling along y-axis through sy. So once the scaling is done, I'll bring it back to the original position. I'll bring it back to the original position, the reverse of that, the reverse of rotation, the inverse rotation. So first I'll rotate so that it will interact x-axis and y-axis. After that, I'll perform the scaling. After that, I'll bring it back to the original position. So these are the operations. That is, after the scaling is performed, I'll just rotate this object in the opposite direction so that it will come to the original point. So what is the sequence of operation means that you can check here. See, the first thing is rotation. After that scaling, first perform the rotation, perform the scaling, and the last thing is perform the inverse rotation, that is rotating in the reverse direction. So for this they're given the product, they have given the product of these three factors, but you know what is r, you know what is r, you know what is s, and you know what is t. So you should know the formulas for rotation, you should know the formulas for transformation, and also for example, we know that r is given by cos theta minus uh, sin theta cos theta 0 0 1. It is represented like this. So one factor is cos like this. Then scaling will be along x-axis, y-axis. No, scaling along x-axis, y-axis 0 0 0 1 0 0 0. You should remember this. You should remember this. And t is given by t is given by what is t? What is t given by the transform translation? No, one one 1, here it will be tx, ty 0 0. So this we have studied in two dimension thing, two dimension translation value, rotation, scaling. The same thing for r inverse. For r inverse, what they would have done means, for r inverse, I'll just show this. See, this is the final equation which you have obtained. But how this equation means, r inverse means, for this, wherever positive sign theta is there, replace it with minus theta. Cos of minus theta will be cos theta. Sine of minus theta will be minus theta. Minus into minus will become plus sine theta. So 0. Again, sine of minus theta will be minus sine theta. Cos of minus theta will be cos theta. 0 0 0 1. So first line is, this is r inverse of theta. So after this, yes, this is scaling along x-axis, scaling along y-axis. So wherever x is there, replace with s1, s2, 0 0 0 0 0 0 1. So after this again, the r of theta means cos theta, sin theta, 0, sin theta, sin theta, cos theta, 0 0 0 1. Sin theta will be, here it will be minus sin theta. Sorry, 1 second. Minus sin theta, sin theta. So if you perform the matrix multiplication of these three things, you will get the final result. You can just cross verify. You can just cross verify. So you will obtain this. So if you perform the multiplication of these three matrices, this will be the final transformation matrix. This will be the final transformation matrix which you will be obtaining. So this is the general two-dimensional scaling direction. This will be the general two-dimensional scaling direction. You just look into this. You just look into this for a minute. I'll just I'll just you just look into this. After that, we'll just derive this. We'll just derive this. So this is the matrix. So if you can if you want to know the result means, you can just verify this. So I'll just verify this as fast as possible, the result. So first thing is cos theta into s1, cos theta into s1 plus 0. So you will get s1 cos theta s1 cos theta. See the first I'll do the multiplication of these two, matrix 1 and matrix 2. Just think s1 into cos theta. The first line will be s1 cos theta. After this, the root 0 0. So 0 s2 sin theta. The second line will be s2 sin theta. Again, the other things will be 0. Again 0 0 0. The last line will be 0. So after that, minus s1 s1 sin theta minus s1 theta 0 minus 0. Again s2 cos theta. Again 0. Last line will be 0 0 0 0 0 0 and 0 0 1. So 0 0. So this will be the product of these two, product of 1 and 2. So after this I have to multiply this with cos theta sin theta 0 0 1 sin theta cos theta 0 0 1. So if I multiply this, s1 into cos theta will become cos square theta plus plus s2 sin square theta. So the first product 0 into 0 will be 0. Again s1 cos theta sin theta, it will become minus s1 cos theta sin theta. After that, the second one will be plus s2 cos theta sin theta. Again 0. So again this one minus s1 sin theta cos theta minus s1 sin theta cos theta, plus s2 cos theta sin theta. Again minus s1 sin square theta plus s2 cos square theta. Again 0 0 0 1. So see the result s1 cos square theta, s2 sin square theta. This is what the result is which I have derived now. So this is how the two-dimensional scaling matrix result which we have obtained. So this here they have rearranged the term. They have taken sin theta cos theta common and s2 minus s1. That's all. So the last term is rearrangement. So this is how you have got the translation matrix. So just remember that whenever a two-dimensional matrix scaling is to be done, the first thing is you have to align it with the x-axis and y-axis. After that, you have to perform the scaling, and again the reverse rotation. Reverse rotation means changing it back to the initial position. So this is how. So based on all these things, we'll solve one problem so that it will be easy to remember. The next thing is how like the composite transformation matrix and computational efficiency. So transformation matrix and computational efficiency means, see here, here I've written one transformation matrix. Here I've written one transformation matrix. See this matrix, it is a combination. So this matrix is a combination of rotation, scaling, translation. Here R indicates rotation, S indicates scaling, and T indicates translation. So a two-dimensional transformation matrix which consists of any combination of translation, rotation, and scaling is given by this equation. It is given by this equation 1. So here we have four elements. Here we have four elements: rs, 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 rs. The first four elements with rs and subscript jk, where the j can be x, k can be y, or combination. So the first four elements, the first four elements. So here the two-dimensional transformation matrix, which consists of any number of any combination of translation, rotation, scaling, is expressed in this form, which is represented by the equation 1. So here I have given the first four elements, that is, which is represented by rs with the subscript jk. So what are they? Means they are the multiplicative rotation scaling terms. So these are the multiplicative rotation and scaling terms. So R will be multiplication rotative term, and S will be SXX, XY, YX, and YY. There the multiplicative scaling term. So R indicates rotation term and S indicates scaling term. So means here R will perform only rotation angle. R consists of rotation angle, and this scaling will be like scaling along x-axis, scaling along y-axis. So that is taken care by S, XX, XY, YX, YY. So the same thing, the same thing, the same thing. We will expand this. The same thing will expand this. You know that R is given by cos theta. Just now you studied, no, cos theta, sin theta, cos theta. So see here we have studied that this is minus, no, r inverse, no, cos theta minus sin theta cos theta. So cos theta sin theta, r will be given like this only. So you can check wherever r is there, you're writing with cos theta minus sin theta cos theta. And yes, what is yes? Yes consists of scaling along x-axis, scaling along y-axis. So scaling along x-axis, scaling along y-axis, scaling along x-axis, scaling along y-axis. So the first four terms are the multiplicative scaling terms, multiplicative rotation terms. So R will perform only rotation angle, and the remaining S will perform the scaling. And the elements and the last two elements and the last two elements and the last two elements is there. No, the last two elements are given by transformation, translation, rotation, scaling. Translation, rotation, scaling. Uh, Translation, rotation, scaling. So translation, rotation, scaling. So these terms consist of translation distance, rotation about a pivot point, rotation about a pivot point, and scaling along a fixed point, scaling along fixed point. So the last two terms, TRSX and TRSY, it will consist of translation term, rotation term. Sorry, the translation consists of translation distance, pivot point value, fixed point value. So for example, if you want to, so now we know about the terms. Now we know about the terms translation, rotation about a pivot point, rotation scaling along a fixed point, scaling along a fixed point. So for example, now you want to rotate an object. So now you want to scale an object and you want to rotate that object along a point, along a coordinate point called xc comma yc. So you want to you want to scale an object, 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 you want to rotate an object about the point xc yc and about the pivot point xc yc by an angle theta. So you want to scale an object, you want to rotate an object about the coordinate position xc comma yc. After that you want to do the translation. So for that what is the matrix means, this is the result. For this the matrix will be written like this. So this is the resultant matrix. So you want to perform translation, you want to perform rotation, and also you want to perform the scaling. So you want to perform the translation, you want to perform the rotation, you want to perform the scaling. The translation will be along tx ty, rotation along the points, pivot points xc yc, they are given the points, and also scaling along the points xc comma yc. So now how to write the matrix? How to write the matrix means, see, from here we can write the matrix. From here, from these points we can write the transformation matrix. How means, what is the first term? R and S, rotation scaling. So R contains rotation angle. R contains rotation angle. R contains rotation angle. That rotation angle is given by cos theta minus sin theta, cos theta. So we got the rotation value. We got the rotation value, and also scaling along x-axis, scaling along y-axis. So Sx, Sy. So because the first four terms consists of rotation plus scaling. So we know that rotation is given by cos theta, sin theta, cos theta, and scaling along is given by Sx, Sy, Sx, Sy. So first four terms are about the same thing. So since it is to be scaled and rotated, Sx cos theta minus Sy sin theta. Again Sx sin theta, Sy cos theta. The last will be 0, 0, 1. So these 4 points are clear. So this is how the first 4 points are derived. Sir, how about this? How about these two? How about these two? How about the last two? So how to derive those last two means, how to derive those last two values means, the last two values are given by, the last two values are given by, the last two values are given by the terms, the last two values are given by the terms tr sx, tr sy. So t means translation tx or ty, rotation about some pivot point xc, yc. S means scaling along a fixed point xc, yc. So now let us go back to few equations. Let us go back to the previous equations where we have generated an equation, like how to generate, how to get the equations for scaling about a fixed point and rotation about a fixed point. So that equation, one second, I'll go to that slide. I'll go to that slide. Hmm. See, this is one direct. This is one thing. The scaling about, the equation about, the equation about the the fixed point scaling, and for rotation also, you can check, for rotation also you can check rotation about this is the rotation about the what do we call, this is a rotation about a pivot point. So you just remember this equation, you just remember this equation. What is the equation given here? What is the equation given here? um, what is the equation given here? The equation is given by xr into 1 minus cos theta plus yr into 1 minus sin theta. So you just remember the equation one, these two values. So now we'll go to this line. Now we'll go to the our equation. Now we'll go to our equation. So now how they have generated, this. So the equations which we saw were like some xr into 1 minus cos theta plus yr into sin theta. The second equation was yr into 1 minus cos theta minus xr sin theta. So now you don't worry about the translation. That is, you have to add it. So now we are rotating about the centroid xc. So write xc into 1 minus, instead of cos theta, you are rotating and scaling. So instead of cos theta, you should write s x cos theta plus yr is nothing but yc. Sin theta will be like, what is sin theta associated with? Sy sin theta. So sy sin theta plus the translation value will be tx. The translation value will be tx. The same way, the second equation yr will be yc into 1 minus cos theta, no? Sx cos theta plus minus xr. So xr means xc, sin theta means sy sin theta plus ty. So that is how this equation is generated. That is how this equation is generated. From the rotation about a fixed point, we can able to generate this. So you don't see, it's not about biating, it's about understanding. So if you understand those three basic transformation formulas, so the same thing you can extend it. The same thing you can extend this to uh, the composite transformation also. So that one point I just wanted to tell, so I just derived that. So see, after this, so this will be the final equation. So this will be the final equation. So where x dash um, so this will be the final equation. This will be the final equation. So where x dash, so x dash is equal to this factor into this factor. So like x into r xx plus y into r yes xy. So plus tr sx. So that is what I've written. That is what I've written here. and the same thing if you perform the matrix multiplication. So this is the transformation matrix which you will get, which can deal with any number of rotation, any number of scaling, and any number of translation. So so like see here, here it required around here this equation required, here um, this equation, no, what is this equation called? um, Equation 1. So this equation required around 9 multiplication, like each row was getting multiplied and around 4 additions or 6 additions. And the same thing can be reduced. The same thing in this form can be reduced to 4 multiplications plus 2 additions. That is means that is how you're improving the efficiency. The computation efficiency is being getting improved. So because the first equation required around 9 multiplication and 6 addition, once it was transformed, the transformed one required only 4 multiplications and 4 addition. So this is how the computational efficiency could be increased. So this is regarding the two-dimensional composite transformation, composite computational efficiency. What is this rigid transformation means? The same equation in this scaling is there, no? If you remove the scaling, so rigid transformation in the sense, the value doesn't change. The value doesn't like the object doesn't get distorted. So whenever the scaling is not there, so it can be, we can call this transformation as the rigid transformation, the transformation which involves only translation and rotation, then we can call it as a rigid body, because when you scale an object, then only it will get deformed. So any operation which involves only translation and rotation, you can call it as the rigid body transformation. For the same equation, if you remove this, if you're removing the scaling terms, so this will become there are 2D rigid body transformation. So it can become the 2D rigid body transformation. So here also the first four elements, 1 2 3 4, where r xx xy yx and yy. So they are the multiplicative rotational terms. So here also the first four elements are the multiplicative rotational terms, and the next two t rx t ry. So these are the translation terms. These are the translation terms. So these are the translation terms. So one thing is, you should you know that here the uh, object doesn't change. So it is so this will call it as the rigid motion transformation. So the angles and the distance between, here the angle between the two edges, the angle or the distance between the coordinate positions will remain same. So it will remain the same. And also one property is there, and also there is one property. So if you consider these four elements, so one property is there for this rigid body transformation. So if you consider the first four matrices, so that is a 2 cross 2 matrix, it is an orthogonal matrix. Which means that if you consider the first row rxx rxy, and if you consider the next row ryx and ryy separately. So if you consider this first row of the matrix as a vector, if you are considering the first row of a matrix as a vector, then these two will form a set of orthogonal vectors. So if you consider this as one vector and this as another vector, then these two vectors will form an orthogonal set of unit vector, meaning so if you multiply this r, so that is what it is written. So the equation is like rxx into rxx will become r square xx plus 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 r rxy will become r square xy, which is equal to 1, again r yx into r xx plus ryy into rxy will be equal to what ryx ry this term plus this term will be equal to 0. So this is the this is the what do we call, this is the which we'll call it as orthogonal unit vector or orthonormal vector set. The same way this is for the first matrix. This equation is for the first matrix. For the second matrix, for the second matrix, rxx ryx plus rxy ryy is equal to 0, and again r square yx plus r square yy will be equal to 1. See, that is when you are multiplying with different coordinates, it will be 0. When you are multiplying with the same coordinates, you will get the result as 1. So that is the terminology. So if the vectors are perpendicular to each other, then it is a dot, then the dot product of that vector will be 0. So this is the definition, this is the definition of unit vector. So this definition they have converted into a matrix form. So this we know that r square xx plus r square xy is equal to 1, and r square yx and r square yy is equal to 1. So the same thing they're splitted up in matrices form. They're splitted up in matrices form. Since we know these two equations, since we know this equation, so the unit vectors will be transformed by the rotation submatrix, where this vector where this vector rxx and rxy is converted into a unit vector along x-axis, and the vector ryx and ryy is transformed into a vector along y-axis. So this is the equation for vector along x-axis, and this is a transformation matrix for equation along y-axis. Mm, so that is what. So this is how the equation is being uh, generated. And also, so if you want, on one example for this can be like one example for this can be like so if you want to this is rigid, no scaling will not be there. So if you want to rotate an object, at positions xr comma yr with an angle theta, and you have to perform the translation along tx and ty. How to do that means Rx what it contains? Only rotation. Rotation means cos theta minus sin theta, cos theta. You know that 0, 0, 1. And only thing is we have to find this. So this we have already studied. Um, this is rotation along a pivot point and rotation along a pivot point. What is that equation? This is 1 minus cos theta, plus yr sin theta. So it is xr into, so this will be yr. So this will be yr xr into 1 minus cos theta plus yr sin theta. No. So the same way for here, we're performing along x-axis. Now xr into 1 minus cos theta plus yr sin theta. For that, you just need to add the transformation term tx. This will be like yr into 1 minus cos theta minus xr sin theta plus transformation matrix ty. So this is how the last two terms. See, the first four terms you can derive it from the definition itself, but for the last two terms, you should know this equation. If you know this equation, for this equation, if you add tx and ty, you'll get the final transformation matrix. So you can check here. So here you can check here. So this is an example. So here, so this figure is an example. This figure is an example where uh, where uh, where you are using the vectors u and v, which are supplied with values like cos theta, sin theta, mm, for the transformation. So what it is doing means here this figure is being or this figure is being rotated from the position. Here it is rotated from from here. It is rotated from this position to this position. So it is an example. It is an example of constructing the 2D rotation matrices. So whatever we have studied now, whatever we have studied in the previous equation, the same thing is being applied. Also here, what we are supplying means, see, also here, what we are supplying means, here we know that this is along x-axis, y-axis. So, mm, so here we are supplying this with cos theta, sin theta minus sin theta, again sin theta, cos theta, 0 0 1 0 0 1. After this rx ry, no, rx, what is rxx? Cos theta, rxx is cos theta, sin theta minus sin theta, again 1, again 1, is equal to 1001. So that is how. So um, that is how the equation is being uh, derived. So that's also here just an example where the first unit vector along the x-axis taking the value cos theta minus sin theta, and the second unit vector is taking sin theta and cos theta. And if you verify that cos square theta plus sin square theta will always be 1. So this is an example um, of this 2D rigid body transformation. So this figure is, it's a rotation matrix. It's a rotation matrix for rotating an object from the position given in figure 1 to a position given in figure 2, which is constructed through the unit vectors u and v with respect to the original orientation in figure 1. We're constructing the figure 2 with respect to the unit vectors u dash and v dash. So this is regarding the 2D rotational uh, 2D rotational matrices. So so till now we have studied everything we have studied with respect to the theory part. Now we'll solve some examples. So this might come in this is for knowledge point of view. I don't know whether it will come in examination or not, but we should have some understanding about the transformations and all. So we'll go with some examples for rotation, scaling, and all. So first thing is we'll go with the translation. The first thing is we'll go with translation. So for example, we'll consider 1, 2, 3, 4. Again 1, 2. So now now this square is there. Now this square consists of 4 points, 4 coordinates, coordinate 1, 2, 3, 4. So I'll take coordinate 1 p naught as 0 comma 0. So this is 0 comma 0, and this will be p1 will be 0 comma 2, mm, 0 comma 2. This is p naught, p1, p2. p2 will be p2 will be x is 0, and y is, sorry, y axis, no, it will not be um, So the position of this is 2, no? So it is 2, so it will be 0 comma 2. 1 second. So see, this is wrong. This is, I have written wrong. This is 2 comma 0. X is at the distance 2, but y is 0. Sorry. So this is 2 comma 0, 2 comma 0, and the last point is P3, which will be 2 comma 2. So this is the coordinate 0 comma 0. X is also 0, y is also 0. But here y is 2. Here y is 2, so x is 0. This is 0 comma 2. This is 2, x is 2, y is 2. But here x value is 2 and y is 0, but I written it in the reverse order. So I'm sorry for that. So 4 points are there. So for the square we have 4 points. So now I want to translate this with x-axis and y-axis. So for tx I will give it as 2 and ty I will give it as 3. Increase the value of x by 2 and increase the value of y by 3. So now I have to translate this with respect to 4 points. So with respect to 4 points I have to translate, and then I have to construct the square. So what is the formula? X dash is equal to x plus tx, y dash is equal to y plus ty. So for the for the first point, x is 0, y is 0. So x dash is equal to 0 plus 2, y dash is equal to 0 plus 3. So the first scenario, I'll get the point as 0 plus 2 is 2, 0 plus 3 is 3. So 2 comma 3. So now I'll just construct this 0, 1, 1, 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. So initially 0 comma 0 was there. No, I'm getting it as 2 comma 3. X is 2, y is 3. So this is the point. So this is my new p dash of 0. So this is p dash of 0 point, which is uh, 2 comma 3. This is 2 comma 3. So like this, I'll calculate for, like this, I'll calculate like this, I will calculate for, like this, I'll calculate for second point. Second point is x is 2, y is 0. So x dash is equal to uh, 2 plus 2 plus 2. Y dash is equal to 0 plus 3. So I'll get it as 4 comma 3. I'll get it as 4 comma 3. So x value is 4 and y value is 3. So here I'm getting that point 4 comma 3, 4 comma 3. So see, if anything is missing, you just let me know. The first one is 2 comma 3 and the second one is 4 comma 3. So after this, I'll consider the third one. I'm writing the equations directly. I'm writing the formula. Actually, I have to substitute with this formula, since for the first one I've derived it with the formula. I'm writing it directly. When it is P2, x is equal to 0, y is equal to 2. So now x dash is equal to 0 plus the scaling value 2, y dash is equal to y plus the scaling value 3. So it will be 2, 5. So x is 2 and y is 5. So this is 1.2 comma 5. So after this, the last value, the fourth one, the last value, fourth one, what is that? X is 2, y is also 2. X dash is equal to 2 plus 2, y dash is equal to 2 plus 3. So it will be 4 comma 5. So x is 4 and 5, 4 comma 5. So this will be, this is how the object will be translated. So initially the object was at this position. Initially the object was at this position. The square was in this position. So after performing the translation, it has changed its position. It has changed its position. The square was at the origin. Now I'm moved it to a position where the starting vertex is at 2 comma 3. Any doubt here? Any doubt? Any doubt? See, today we have spoken about three concepts. One is the general two-dimensional scaling direction. How do you scale that? The second one is computational transformation, the computational efficiency for two-dimensional composite transformation, two-dimensional rigid body transformation. Then one example problem to perform the translation. So this is regarding the translation. So in the next class, we'll talk about one example. We'll solve one example related to rotation, scaling, uh, and all. So any doubt here? Any doubt? Any doubt? Any doubts? Okay, 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 fine.